Hi, my name is Josh, and I am part of Team 16 along with Brandon, Seth, Daniel, and Jonah. CFD Research drafted this team with creating an RFID system that could determine generated chirp reflections off a capacitively loaded surface to measure changes in resonant frequency of a sensor. The design is split into two main circuits. The first portion is the transmitter, which is connected to a voltage-controlled oscillator, a power amplifier, and a transmitting antenna. The second portion is the receiver. The receiver contains a PCB with series components of coupled line bandpass filter, a low noise amplifier, and an envelope detector. Now, Brandon will discuss the transmitter.
So for the transmitter, we have an output of a triangle function at 10 kilohertz using an op-amp integrator and op-amp Schmitt trigger to generate the required frequency of the output, level shifters to apply the correct voltage parameters. This linear waveform is applied at the input of the VCO, which it then generates a chirp ranging from 5.5 gigahertz to 5.8 gigahertz. This chirp is applied to the input of a power amplifier to increase the power and finally into the antenna. Next will be Jonah introducing the receiver.
Hi, my name is Jonah and I'm going to be talking about the receiver portion of the board. So the backscattered chirp signal, which is received from the tag, is received by an antenna on the receiver board, and this received signal is then run through a amplifier, which is a low noise amplifier and has a gain of about 20 decibels. And this amplified signal is then filtered with a coupled line bandpass filter, which has a bandwidth of about 5.5 to 6.1 gigahertz. And this filtered signal is then amplified even more by two other identical LNAs, which gives the system a gain of 60 dB. And after these two LNAs comes a microstrip envelope detector, which is supposed to detect the envelope of the carrier frequency and demodulate it. And then this demodulated signal is run through the DSP portion, or digital signal processing portion of the board, which is going to be talked about by Seth and Daniel.
Hi everyone, I'm Seth Dunbar. I'm an online student in Washington, D.C. The next component in the receiver is the digital signal processing, or DSP, subsystem, which we will be using to calculate the resonant frequency of the target. So in order to do this, first we're going to be taking the analog signal and digitize it by using an analog to digital converter. Then the microprocessor is going to detect the peaks in the reflected signal, and it's going to measure the number of samples in between the peaks. Now, since we know the sampling rate, the ramp signal period, and the frequency range of the VCO, we're going to take all this information and use it to calculate the resonant frequency of the target. Next up, we're going to have Daniel, and he's going to be talking about our testing plans for this project.
Hi, my name is Daniel, and I'll be talking about system test. So far we've talked about the functions of all the major components of the system, but an important part of the design process is system test. And not just testing the system at the end when everything is completed. We want to test iteratively and continuously throughout the entire design process. In software engineering, this is referred to as test-driven development. So we've been building a number of test rigs, both in hardware and in software, so that we can test each component individually while the rest of the system is being built. An example of one of these test rigs for the DSP system can be seen over here next to me. But we'll go through that in more detail during the longer presentation. Okay, so to recap and close us out, Joshua and Brandon talked about the transmitter. Jonah covered the RF portion of the receiver. Seth covered the DSP portion of the receiver. And I discussed our team's test strategy. Thank you.